Welcome to Animal Manufacturing Incorporated. It's Monday morning and the factory floor is complete chaos. Machine number 3 just stopped. Again. The rabbits are standing around waiting. The foxes in quality control have nothing to inspect. And over there? That's a pile of defective products that somehow made it through yesterday. The manager just asked me the million-dollar question. Why do our machines keep stopping? And how do we measure if we're actually being productive? Well, my friend, that's exactly what we're here to talk about today. I'm Gary, your industrial engineer, and today we're diving deep into OEE, overall equipment effectiveness. By the end of this video, you'll understand exactly why machines stop, how to measure it, and what numbers actually matter. Let's get started.
So what exactly is OEE? OEE stands for Overall Equipment Effectiveness, and it's the gold standard metric for measuring manufacturing productivity. Think of it as your machine's report card, but instead of getting grades in math and science, your machine gets graded on 3 critical questions. First, was your machine actually available and running when it was supposed to be? That's availability. Second, when it was it running at full speed or was it going slower than it should? That's performance. And third, of all the products it made, how many were actually good quality versus defective? That's quality. These 3 factors, availability, performance, and quality, they multiply together to give you one powerful number, your OEE score. And here's the thing, world-class factories aim for 85% OEE. Most factories, they're sitting somewhere between 40 and 60%. There's massive room for improvement, and it all starts with understanding these 3 components. Here's the formula you need to memorize. OEE equals availability times performance times quality. It's a multiplication, not an addition, and that detail is absolutely critical. We'll come back to why later. Each of these 3 factors is calculated as a percentage. So if your machine was available 90% of the time, ran at 95% of its ideal speed, and produced 98% good quality products, your OEE would be 0.90 times 0.95 times 0.98, which equals about 84%. That's actually pretty good. But notice something important. Even though each individual number looks great, 90%, 95%, 98%, when you multiply them together, you end up with 84%. That's the brutal math of OEE. Every loss compounds. A small problem in availability combined with a small problem in performance, combined with a small problem in quality, and suddenly you're losing 16% of your potential output. That's why OEE is so powerful. It forces you to see the true picture. Let's break down availability first, because this is where most factories lose the most time. Availability answers one simple question. During the time your machine was supposed to be running, how much time did it actually run? Let's say your shift is 8 hours. That's 480 minutes of planned production time. But during those 480 minutes, your machine had a breakdown that took 30 minutes to fix. Then there was a changeover to a different product that took another 20 minutes. Then someone had to wait 10 minutes for raw materials to arrive. That's 60 minutes of downtime. So your actual runtime was only 420 minutes. Your availability is 420 divided by 480. which equals 87.5%. Now here's what most people miss. Availability only counts downtime during planned production time. If your machine is scheduled for maintenance on Sunday, that doesn't count against availability. We're only measuring when you plan to produce, did you actually produce? Breakdowns, changeovers, material shortages, waiting for approvals, all of that is availability loss. Let me show you what availability loss looks like in real life at our animal factory. This morning, machine B broke down at 9 a.m. We called Steve the sloth from maintenance. Now, Steve is great at his job, but he's methodical. By the time Steve diagnosed the problem, found the right parts, and fixed the issue, it was 10:30 a.m. That's 90 minutes of downtime. Meanwhile, the rabbits at the next station have nothing to work on, so they're just standing there. That's availability loss, pure and simple. The machine physically could not run. Now later in the day, we had to switch from making blue widgets to red widgets. That changeover took 25 minutes. Again, the machine is stopped. More availability loss. Then at 2 p.m., we ran out of raw material because the supplier delivery was late. The machine sat idle for 40 minutes waiting. You see the pattern? Breakdowns, changeovers, material shortages. These are your availability killers. And the scary part, most factories don't even track this properly. They just know the machine stopped sometimes, but they don't measure how much time is truly lost. Now let's talk about performance, and this is where things get sneaky. Performance measures. When your machine is running, is it running at full speed? Every machine has something called an ideal cycle time. That's the theoretical fastest speed it can run at when everything is perfect. Let's say your machine is designed to produce 100 units per hour. That's your ideal. But in reality, you're only getting 75 units per hour. Your performance score is 75 divided by 100, which equals 75%. So what causes performance loss? Small stops. The machine keeps pausing for 5 seconds here, 10 seconds there. Maybe a sensor is acting up, reduced speed. Maybe the operator slowed it down because the material is slightly off spec, and running full speed causes jams. Minor adjustments, stopping to tweak settings. Operator inefficiency. Maybe the new guy doesn't know the machine as well yet. Here's the key difference between availability and performance. With availability, the machine is completely stopped. With performance, the machine is running, it's just not running as fast as it should be. Both cost you money, but performance losses are often invisible unless you're actively measuring. Back to our factory. Meet Milo the monkey. Milo operates machine C, which is supposed to stamp 100 metal parts per hour. But today, something's off. The machine keeps making these tiny little pauses. 3 seconds here, 5 seconds there. Nothing major, it's not a full breakdown. But by the end of the hour, Milo's only produced 75 parts instead of 100. That's a 25% performance loss. When Gary investigates, he finds several culprits. First, the photo sensor that detects incoming parts is dirty, so it's causing micro stops. Second, the lubricant in the machine is old, so the mechanism is running slightly slower than it should. Third, Milo adjusted the speed down to 90% because he noticed the parts were getting slightly scratched at full speed. He was trying to help, but it's still a performance loss. None of these issues stopped the machine completely, but they're killing productivity. This is why performance is so important to track. If you only measured availability, you'd think everything is fine. The machine was running all day, but you're losing 25% of your output to invisible speed losses. Finally, we have quality. Quality measures of all the parts you produced, how many were actually good. This seems simple, but it includes more than just obvious defects. Quality loss includes fully defective parts that go straight to scrap. Those are total losses. But it also includes parts that need rework. If you made a part and it came out wrong, and now someone has to spend 10 minutes fixing it, that's a quality loss because you consumed time and materials and didn't get a good part the first time. Let's say you produced 420 units during your shift. Out of those, 390 were perfect first-time quality, but 20 units had defects and went to scrap, and 10 more units needed rework before they could be shipped. Your quality score is 390 divided by 420, which equals about 93%. Now here's a critical point. Quality is measured at the end of the process, but quality problems often start much earlier. Maybe the raw material was slightly off spec. Maybe the machine calibration drifted during the day. Maybe an operator made a setup mistake on hour 2, and you didn't catch it until hour 5. All of that shows up in your quality score. Let me show you what quality loss looks like in action. Francesca the Fox is our quality inspector. At the end of today's shift, she inspects all 420 parts that came off machine D. Out of 420 parts, she finds 20 that are completely unusable. They have cracks, wrong dimensions, or failed stress tests. Those go straight to the scrap bin. That's wasted material, wasted machine time, wasted labor. Then she finds another 10 parts that are borderline. They're not perfect, but they can be fixed. Those go to the rework station where Randy the Rabbit will spend an hour sanding them down and repainting them. That's more wasted time. So out of 420 parts made, only 390 were right the first time. Gary investigates and discovers the root cause. At the start of the shift, someone adjusted the machine settings incorrectly. For the first 2 hours, the machine was producing defective parts, and nobody noticed until Francesca started inspecting. That's 120 units of production time where every single unit was either a scrap or a rework. This is a classic quality failure. The machine was available, the machine was running at full speed, but it was making garbage. Now here's a question students always ask me. Gary, why does OEE multiply the 3 factors instead of adding them? Great question, and the answer is crucial. Let's say your machine has 90% availability, 95% performance, and 98% quality. If we added them, we'd get 283%, which makes no sense. You can't be 283% effective. But more importantly, addition doesn't capture how losses compound. Here's the reality. You start with 480 minutes of planned time. After availability losses, you're down to 432 minutes of actual run time. That's your 90%. But during those 432 minutes, you're running at only 95% of ideal speed. So you're really only getting the equivalent of 410 minutes of perfect production. That's your performance hit. And of those 410 minutes worth of production, 2% of the products are defective. So you only get credit for 402 minutes of good output. The losses stacked. Each loss happened on top of the previous loss. That's why we multiply. The final formula is 0.90 times 0.95 times 0.98 equals 0.84 or 84% OEE. You lost 16% of your potential output, not because of one big problem, but because small problems in each area compounded each other. All right, let's run through a complete real-world OEE calculation from start to finish with actual numbers. We're analyzing an 8-hour shift, which is 480 minutes of planned production time. First, availability. During the shift, the machine had 30 minutes of breakdown time, 10 minutes of changeover time, and 8 minutes waiting for materials. That's 48 minutes of total downtime. So run time is 480 minus 48, which equals 432 minutes. Availability is 432 divided by 480, which equals 90%. Next, performance. The machine's ideal cycle time is 1 unit per minute. So in 432 minutes of runtime, we should ideally produce 432 units. But we only produced 410 units. Why? Small stops, reduced speed, minor adjustments. Performance is 410 divided by 432, which equals about 95%. Finally, quality. Of the 410 units we produced, we inspected them and found 368 were good quality. 30 units were scrap and 12 units needed rework. Quality is 368 divided by 410, which equals about 90%. Now the final OEE calculation, 90% availability times 95% performance times 90% quality equals a 77% OEE. That means we achieved 77% of our theoretical maximum output. We left 23% on the table due to downtime, speed losses, and quality issues. So how do managers actually use OEE in the real world? First, as a diagnostic tool, if your OEE is low, you can immediately see which of the 3 factors is the biggest problem. Is it availability? Then focus on reducing downtime. Fix those breakdowns, speed up changeovers, eliminate waiting. Is it performance? Then investigate speed losses. Clean your sensors, maintain your equipment, train your operators. Is it quality? Then dive into root causes of defects. Check your materials, calibrate your machines, improve your processes. Second, OEE is used for benchmarking. You can compare machine A to machine B or compare your factory to industry standards. World-class manufacturing is 85% OEE or higher. If you're at 60%, you know there's significant room for improvement. Third, OEE is used to track improvement over time. Did that new maintenance program actually reduce downtime? Did the operator training improve speed? Did the quality initiative reduce defects? OEE gives you a single number that captures the overall impact. And finally, OEE helps prioritize resources. If machine X has 50% OEE and machine Y has 80% OEE, you know where to focus your improvement efforts first. Before we wrap up, let me tell you the most common mistakes people make when calculating OEE, because I see these all the time. Mistake number 1, counting unplanned time as downtime. If your shift is 8 hours, but there's a 30-minute lunch break, your planned production time is 7.5 hours, not 8. Don't count lunch as downtime. That wasn't production time in the first place. Mistake number 2, using the wrong ideal cycle time. Your ideal cycle time should be the design speed of the machine, not some aspirational number and not the average speed you've been running at. It's the theoretical maximum. Mistake number 3, not tracking small stops. Many factories only track major breakdowns, but they ignore all the little 2-minute, 5-minute stops throughout the day. Those add up to massive performance losses. Mistake number 4, not counting rework in quality losses. If a unit needed to be reworked, it wasn't right the first time, so it counts as a quality loss, even if it was eventually fixed. And mistake number 5, gaming the system. I've seen operators slow down the machine on purpose to make performance look better, or declare more downtime than actually occurred to make availability look worse so they can blame maintenance. OEE only works if you measure honestly. Before we wrap up, let me tell you the most common mistakes people make when calculating OEE, because I see these all the time. Mistake number 1, counting unplanned time as downtime. If your shift is 8 hours, but there's a 30-minute lunch break, your planned production time is 7.5 hours, not 8. Don't count lunch as downtime. That wasn't production time in the first place. Mistake number 2, using the wrong ideal cycle time. Your ideal cycle time should be the design speed of the machine, not some aspirational number, and not the average speed you've been running at. It's the theoretical maximum. Mistake number 3, not tracking small stops. Many factories only track major breakdowns, but they ignore all the little 2-minute, 5-minute stops throughout the day. Those add up to massive performance losses. Mistake number 4, not counting rework in quality losses. If a unit needed to be reworked, it wasn't right the first time, so it counts as a quality loss even if it was eventually fixed. And mistake number 5, gaming the system. I've seen operators slow down the machine on purpose to make performance look better or declare more downtime than actually occurred to make availability look worse so they can blame maintenance. OEE only works if you measure honestly.